Today's video we'll be solving LeetCode's problem number 162, which is called Find Peak Element. It's a medium difficulty problem, and let's quickly read the description. So, a peak element is an element that is strictly greater than its neighbors. Given a zero-indexed integer array called nums, find a peak element and return its index. If the array contains multiple peaks, return the index to any of the peaks. You may imagine that nums of -1 is equal to nums of n is equal to minus infinity. So basically, we can assume that the values around the array are minus infinity, meaning they are strictly less than its neighbors, first and the last element of the array. In other words, an element is always considered to be strictly greater than a neighbor that is outside the array. You must write an algorithm that runs in O of log n time. And here there are a couple of examples. So the first example is the index 1, 2, 3, 1. So it basically goes like this: 1, 2, 3, and then 1. So it has a single peak. In this case, the output should be 2, because the number at index 2 is number 3, and it's basically the greatest element of the array. It's surrounded by 2 neighbors that are strictly less than number 3. That's why number 2 should be returned in this case. In the example number 2, this array has multiple peaks, so 1, 2, 1, 3, 5, 6, 4. So there are multiple peaks. One of them is number at index number 1, which has the value of 2. Another peak is this one at the index number 5 with value 6, and the output could be 5, but it could also be 2 if I'm not mistaken. I mean, if we apply the binary search approach, it should be always 5, but here your function can return either index number 1, where the peak element is 2, or index number 5, where the peak element is 6. So both 1 and 5 are valid responses. And yeah, so 5 is a valid response, so it can return number 5. Besides this description, there are a couple of constraints that we need to be aware of, because those constraints are quite important in this case. So a couple of constraints. So nums.length is at least 1, and it's not longer than 1000 elements. So the length of the provided array is a number between 1 and 1000, including these two boundaries. That means that the provided array will not be empty, neither null. The value of any element in the array is an integer value which can contain negative numbers, so the range of the values is between -2 over 31 and plus 231 minus 1. So that's the range of the possible values of this array nums. And there, the third constraint is also very important constraint, because it tells us that any 2 neighbor values are not equal. For a valid I, nums of I is not equal to the nums of I plus 1. So any 2 adjacent values in the array are not equal. So an integer containing, for instance, the following values 1, 1, 1 is not possible, because any two adjacent values in the array must not be equal. Okay, so let's see how we can implement the solution of this problem. So by reading the description, it suggests that the overall time complexity of the solution must not exceed O of logarithm of n time. So this is the worst case time complexity. So if we have an array, we must not spend more than logarithm of n time to solve this problem in the worst case. So a naive approach that does not have the expected time complexity would have a linear complexity, would be to simply start from the first element of the array and to traverse the array until we find a peak element and we can return it. That approach might be quite efficient for the long arrays where the peak element is somewhere at the beginning. Let's say the peak element is somewhere here and the array is very long. In that case, that linear approach would be very efficient because it will spend not more than a couple of checks at the beginning of the array and it would return the response. However, that's not our goal to be super efficient in certain cases, but our goal is to find a solution that never exceeds O of logarithm n time. So that the same linear approach that I explained. So maybe I can write an example array. So let's say this is an example array, example 1, something like this: 1, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, and minus, I don't know, 1000. So this array obviously has a peak here at the beginning. So a solution that would traverse this array linearly from the start would return the peak element, which is here at the value number 2, relatively quickly. It would check the first element, it would check the second element, and by checking the second element, it can figure out that this is a peak element, and there's no need to check the other elements after the second element or after the first element, if you take this one into consideration, and we can quickly return the output value, which should be 2. However, the same approach, which is the linear approach, so this one has time complexity O of n, where n is equal to array.len. But the same approach, so we can see it's very efficient for this array, input array, but the same approach would not be that efficient for this array. For instance, imagine that the array is something like that, contains values like this. So let's say it's 1, 2, 3, 4, 5, 6, 1000. So this array has a peak at the end. So this is the peak element. Why is this the peak element? Because before 1000 goes 999. So this value is strictly less. This value 1000 is strictly higher than 999, and from the constraints or from the problem description, it said that this array is surrounded with minus infinity. So here is minus inf. So this value is also strictly less than 1000, and this value is also strictly less than 1000. So 1000 is the peak element. So here the output should be 999, which is the index of the last element here. But here the linear approach would need to traverse the whole array and find the output. So that's why this linear approach it is efficient in certain cases, but in the worst case it's not that efficient, because it has to traverse the whole array. It needs to go through all elements of the array. That's why we said that it has a linear complexity, or O of n complexity in the worst case, because in the worst case it has to go through n times to perform n checks in an n-sized array. Okay, so our goal here is not to find a linear time complexity solution, but our goal is to find, as it suggests here, O of logarithm of n time complexity solution. Anytime when we see this time complexity O of logarithm of n, that logarithm of n usually suggests a binary search approach. Why binary search? Because binary search works that it eliminates the half of the array every time in every step. So let's say this is the array of 1000 values, and with binary search it would in only one step it would get rid of the half of the array and will continue the search in the right half of the array, in this particular case in just one step. So it will eliminate the half of the array. With the linear approach, at every step we don't eliminate the half of the array, but only that one single element. So if we have the approach that at every step eliminates half of the array, and then the second step it eliminates half of the array, and so on and so on, we will basically the total number of those steps to reach the end, the final value, will be equal to logarithm of n. It will take logarithm of n steps, and the base for the logarithm is 2, because at every step we are eliminating half of the basically array. So how can we use binary search approach to solve this problem? As a prerequisite maybe for solving this problem for you would be to be familiar with how binary search works. So if you are not familiar, I would recommend you reading some documents or getting yourself familiarized about how binary search works, and that would be useful, so you can understand the solution better. So we will assume that we are familiar with the binary search here. So here is the method that we need to implement. It's called find peak element. It takes an array of integers as an input, and it returns an integer value, which is the index of a peak in this array. So any peak is considered to be a valid response. So let's see how we can implement the binary search approach here. Let's say let's take an example from here. So we have this array which is 1, 2, 3, 1. How binary search works? Well, we will start with the left and right boundaries, which are initially equal to the leftmost and rightmost elements. So left is index of the leftmost element, which is 0, and right boundary r is equal to the index of the rightmost element, which is equal to basically to nums dot len minus 1. Then, how binary search works? We take the middle value of the array, which is called median value, which is equal to, let's say, L plus R divided by 2. And since we are dealing with integer values, this m will always be an integer. So in this particular case, the middle element could be number 2 or number 3, but because we are using we are dealing with integers, and dividing by 2 will take the whole part of the result. So median value should be, if the indexes are 0, 1, 2, and 3, the median value should be 2.5. That's the median value between indexes 0, 1, 2, and 3. I'm sorry, 1.5. Apologize. So it will be somewhere between. But given that m is an integer, L and R are integers also, so the m will be the value which is the whole part of this division, which is basically 1. So this will be the middle element. What can we also notice from this array? We can, or from the problem description, given that this array is surrounded with minus infinity and minus infinity values, so, and given that every single value here is different to the value of its neighbors, so 2 is different than 3 and 1, 3 is different than 2 and 1, and so on, we can say that this array must have at least one peak. So if our array starts from the beginning with the values that are strictly increasing, 1, 2, 3, 4, 5, and if it reaches the end, so there are no peaks here, but at least the last element will be the peak, because after the end of the array goes minus infinity, which is strictly smaller than 5. So, on the other hand, if the array if the elements of the array are decreasing, like 5, 4, 3, 2, 1, then the first element will be the peak. Why? Because the next element is strictly smaller than the first element, but in front of this first element goes minus infinity, and then 5 is the peak. Okay? And finally, if the element, so here the peak is 3, and finally if the elements are going something like this, 1, 2, 3, 4, and then goes a value which is less than the previous value, like for instance 2, 1, etc., then that will be the peak element. So whatever combination of the values of the input array we take, there must be an array, because of these constraints and because of how the problem is described. So there must be, so we know that there must be a solution. So that's one of the most important things that we have to notice, that we need to notice, is that every input array has at least one peak element. So we just need to find it. It can contain multiple peaks, as mentioned here. So this one has multiple peaks. That's fine, but at least it must be one peak element. And when we know that, when we take, for instance, this array as an input, let me move this binary search part because it's related to this one. So one, is this element. So what we need to do, we just need to check the next element, whether it's greater or smaller than the medium element. If it's a greater, if the next element is greater, that means that the peak element has to be somewhere in the right half of the array. Otherwise, if this was the medium element, and if the next element is smaller, that means that we are going down the hill or the mountain, and that means that the peak for this hill or mountain has to be before. And that's all. Given that m is the half of the array, imagine this array is bigger, like -5, apologies, -5, -4, -3, -2, etc. And we are here, or we are here. So we are, the next element is smaller. That means that the peak could be here or could be in the left part of the array. And let's add more elements to the right. And let's say that we are here. We know that the right element, so we are here. For instance, let's imagine the situation. The middle element is here. The right element is smaller than the current element. That means that a peak could be either here or somewhere on in the left half of the array. That means that we can eliminate half, remaining half, the right half of the array when looking. So we can eliminate them all and look for the peak in here, this element, or in the left part. So that's why this approach takes, in the worst case, logarithm of n steps. That's the important thing to notice. So when eliminating a half of the array, another thing to notice, we might be eliminating some other peaks. So there might be some peaks here. There could be some more peaks here. It doesn't matter. We can eliminate them too. But one thing we are sure, that there is at least one peak here or in the left half of the array. That's why we need to, that's the thing that we need to be aware of. So it doesn't matter whether we are skipping certain peaks. It doesn't matter as long as we know that in the direction we are heading to, there is at least one peak, and we need to find the index of it. Okay, so let's try to implement this, and we can also discuss some edge cases too. So how can we implement this solution? So yeah, from the constraints we know that the nums value is not a null value. It has a length which is at least 1. So those are all constraints. Those things are already mentioned in the constraints, so we don't need to make those checks. Or if we want, we can simply say if nums is null, or nums that length is 0, we can throw an exception. Null or empty array provided. Okay, but if it's not a null value, if it's not an empty array, we can go through the array. So let's say int. So let's define the boundaries, initial boundaries for the binary search. We can say int L is 0, int R is nums.length minus 1, the leftmost and the rightmost index. So these are L and R are the indexes of this array, and L is the first element, R is the last element of the provided array. And we can do something like this: while L is strictly smaller than R, and we can calculate the minimum, the medium value. So we can say M is L plus R divided by 2, but if we want to avoid potential overflow, we can more common when writing binary search algorithms, more common way to calculate the median value is to say something like this: int M, like the median value, is equal to L plus the difference between the right and L boundaries, R minus L divided by 2. So to the left value, add half of the distance between L and R. It's mathematically equal to L plus R divided by 2. However, to avoid the overflow, because if we would do L plus R divided by 2, and if L and R are big numbers whose sum exceeds the maximum possible value of an integer, this would lead to an integer overflow, and basically it would lead to an error response, to a bug basically in the approach. So slightly better approach, would be to write the expression like this, where we will never have to strictly sum left and right boundaries values, but we can subtract L from R, divide by 2 to calculate the distance, half of the distance between the boundaries, and just add that half of the distance to the left boundary. So okay, so once we have the median value, and we say because of the because we're dealing with integer values, so this value will be the whole part basically of this division, so it will not be the value strictly between the two integers. It may not be but in that case it will take the left side of this, so the whole part of this median value, as I explained previously. So median is this value. So what do we need to check now? We need to check if the median value is on the part of the hill that goes up, or it's on the part of the hill that goes down. And depending on the on that check, we will decide whether we want to eliminate the left half or the right half of the array. So we will say something like this: if nums of M is strictly less than nums of M plus 1, that means that this, let's say that this is M plus 1, value of the M plus 1 at the index M plus 1. That means that as we are going towards this direction, the numbers are increasing because -3 is greater than -4, and the peak will be somewhere on the right, in the right half of the array. That's why we can say that the new left value will be equal to m plus 1. If that is not true, that means that the next value is smaller than the current value, than the medium value, and that means that we are on the side of the mountain where we are going down. So we need to update the right boundary because the peak will be somewhere in the left part of the array. So r will be equal to m. And once this condition is no longer satisfied, that means that L boundary has reached the R boundary, so they're equal, and basically L will be the solution. Index value at the index L will be the index of the peak of a peak element in the array, because there might be multiple peaks in the array. So we can simply say return L. And that's it. That should be the solution of the problem. Let's quickly just discuss these edge cases. So why L is strictly less than R, why L is updated by adding 1 to the m value, and here R is updating to the m value. So those are some kind of edge cases, not edge cases, but kind of things that you need to be super careful of, because if you make a tiny change here, the whole solution might not be working. So why have I decided to use this kind of binary search setup? Let's call it like that. So first of all, while L is strictly less than R, that means that initially L is the first element, R is the last element, and at every step this m value is somewhere in between. So at every step we are eliminating some numbers from the array, roughly half of the array. But if the first condition is satisfied, if we would keep something like this, we might end up in an infinity loop, because m might always be equal to L, and we will always update L with m, and we will basically end up in an infinity loop. So we need to make sure that with every step we are making a step towards the final solution. On the other hand, when R is equal to m, because when we are dealing with this integer division, so we divided by 2, and this m will always be the whole part of it. So if we have an array that has two elements, 1 and 2, m will be 1, and if R is equal, m will be, let's call it 0 and 1, m will be here, this will be the middle element, and R initially L will be here, and R will be here. So by updating R to m, we are updating right to one step further, or one step closer to the first element, to here, and then R becomes equal to L, and we are ending this while loop. That's why we chose this kind of setup. On the other hand, if we are updating L to L value, we always are going one step closer to the end of the array, and that's why we never gonna end up in an infinity loop. I hope this makes sense. But yeah, I would highly encourage you to play around with this value to try to debug the solution against different inputs, and you'll see how these left and right boundaries are being updated and how m is being calculated, etc. But it's super important if you want to make sure you don't end up in an infinity loop or you are not missing any valid responses. By the way, this should be the solution. I still haven't tried it, so let's quickly try and run it against a certain set of numbers. So let's say something like this: solution is equal to new solution, and here the class solution is where I implemented the solution of the problem in this public method, which is called findPeakElement, which takes an array of integers. So let's create an array of integers. So let's create a couple of test cases. What would be the good test cases? First, let's start with the regular integer value. Let's say integer nums1 is equal to new integer. Let's take the example from here: 1 2 3 1 1 2 3 1, and here let's print the output result nums1 solution dot find peak element nums1. Is 2. Here the solution is 2. Why 2? 0 1 2, because 3 is the peak element. That's correct. Let's take this one: 1 2 1 3 5 6 4. nums2 is equal to new int 1 2 1 3 5 6 4. So result for nums2 is find peak element nums2. This is 5. That's expected. And by the way, do you know why 5 is the output here? Basically, it would always be 5 if we are applying the binary search approach here. Why? Because the middle element is this one, right, with number 3. So there are 2 peaks, one here at number 6 and one here at number 2 at the beginning. But given that 3 is strictly less than 5, the next element, we are eliminating this half of the array. So that's why this peak at index number 1 with the value 2 will never be chosen. And that's why we are basically heading towards a peak in the right half of the array, which is at index 5 with the value 6. Okay, let's find a couple of more. Let's define a couple of more examples. Nums. Let's find an example, for instance, when an element of the array are strictly increasing: 1 2 3 4 5 6 7 8, something like this. And let's print the output for nums3. Find out nums3 So what should be the output? The last element of the array, right? Yes, the element at the number at the index 7, which is this one. Okay, and let's find another edge case example. Nums4 is equal to of, let's take an opposite example. Let's say 4, 3, 2, 1. In this case, the first element should be the pig. Exactly. So, and here we can find a couple of more edge cases. For instance, let's take nums5, which is equal to which has, let's say, which has only one element. Okay. So here, that single element should be at the same time the solution of this problem. So result nums5 is 0. Okay, so it's very important to test your solution against these various edge cases and to make sure it successfully handles all of them. There are a couple of more edge cases that can be added, but also if you're using the LeetCode portal, yeah, you can simply submit your solution there and you will quickly figure out if it passes against all the different test cases. So yeah, I hope that you like this video, and I'll see you in the next video. Thank you all. Bye.